Welcome to another session of topology. Today we will have a discussion on path connectedness spaces. So in the previous session we have seen what is a path. So here 3.6 definition, a path. A path in a topological space is a continuous function alpha from closed interval 0, 1 to the space. So suppose this is going to be a space. Now we'll have a continuous function from this to this space, and suppose this space is something like this is going to be a path, and we will name this as alpha. Now alpha of 0, we will say that is the initial point or the starting point of path, starting point, and alpha of 1, we will say that it is the terminal point or endpoint. Next, what we have seen is this path is sometimes called a curve, but we usually call a curve in the Euclidean spaces. Okay, that is the node one. Then the next one is when we say that a path is a simple one. It's said to be simple if alpha is 1 1. If alpha is 1 1, or we may say that injective, then alpha is simple. So simple path we will say. Okay, now we will say that alpha is simple. Now a closed path means alpha should come, it should start and end at the same point. That is, we have said that initial point or the starting point is alpha of 0. That should be same as the end point. End point is alpha of 1. So whenever alpha of 1 equal to alpha of 0, we will say that this path is closed. So a simple closed path means anyway at the end point alpha of 0 should be equal to alpha of 1. So remaining all the points, it should be 1 1. Okay. So a simple closed path is a closed path alpha that is injective except for alpha 0 equal to alpha 1. That is the initial point and terminal point should be the same. Then the remaining points alpha should be 1 1. Next definition, what is a path connected space? A space X is said to be path connected if for every 2 points x, y in X, there exists a path alpha in X such that means suppose you have got a space over here. This is your space, and you have got some points somewhere here. Now, if we can find a path which connecting these two such that suppose this is x and this is y, then your alpha of 0 should be equal to x and alpha of 1 should be equal to y. If these two conditions satisfied for every x and y, then we will say that this entire space is path connected, right? Thus, a space X is said to be path connected if for every 2 points x, y in X, there exists a path alpha in X such that alpha of 0 is equal to X and alpha of 1 equal to Y. Now, examples are real line. Okay, you take in real line. We are having a point here X, here a point Y. Now, this real line itself will connect X and Y. This itself is a path, right? From alpha is a path. Okay. Now all Euclidean spaces and any convex subset of them are path connected. Very evident, right? Since we have studied that in convex means definition of convex, if this is x and this is y, what you're having is for 0 less than or equal to lambda less than or equal to 1, right? Lambda x plus 1 minus lambda into y also belongs to C, right? Then we will say that for x comma y belongs to C, This also belongs to C, implies C is convex, right? Now what is the meaning of this? Meaning of this is that X and Y lie on a line connecting X and Y, right? All the points in between X and Y are lying in this line. Okay, so that itself will form a path. Next, we will show that a path connected space is connected, right? A path connected space is connected. So we have got a space which is path connected. That means for any two points of the space we can find a path. Then I can fix some x naught, right? X is non-empty. Fix some point x naught. For each x belongs to x, we can give a path. Okay, now suppose here is one x is there, means I can find a path, this path that I am naming as alpha x, right? With the property that alpha x of 0 equal to x naught and alpha x of 1 equal to x, right? That means alpha x is a path connecting x naught to x. Now Cx means the range of alpha x. Now Cx I am denoting range of alpha x, or range of alpha. Alpha is defined from closed interval 0, 1 to our space x, right? So this is the range. Now what about the range of alpha? Is it connected? Yes, of course, it should be connected. Why? Because it is the continuous image of the closed interval 0, 1, and closed interval 0, 1 is connected. So continuous image of a connected set should be connected. So Cx is connected. See here. Let Cx be the range of alpha x. Then Cx is connected. Reason, it is the continuous image of the unit interval which is connected, right? Then we can write our x as union x belongs to x of Cx. Since the space is path connected, there always exists a path between x naught and any point of the space. So you can write your x as union x belongs to x Cx. Now we want to prove that this is connected, right? We assume that this path connected. Now we have to show that x is connected. Now we have to show x is connected. Then previously we have studied one theorem that if the union of such connected set is connected, if they are not mutually separated, that means they should have non-empty intersection. Now suppose I am having a Cx and Cy. That is, Cx and Cy means there's a path alpha x which will connect my x naught to x, and there's a point y. Now I can have a path which connect x naught to y also. Now can I find a path between y to x? It's possible, right? Yes. So let it be there. Now what we need is, will this Cx and Cy has got some intersection? Of course, what should be? It should be alpha of x naught, right? So alpha of x naught belongs to Cx and alpha of x naught belongs to, sorry, it's not the other way, right? X naught. It is the x naught, not alpha of x naught, it is x naught. Okay. Now this Cx and Cy are non-empty, right? Therefore x naught belongs to Cx and x naught belongs to Cy, which implies Cx intersection Cy is non-empty. That means in this collection, these members are not mutually separated. That means this union is a connected state. Hope you understood that one, right? So let us see. We assume that X is path connected space. Now if X is empty, then certainly X is connected. Now suppose X is non-empty. We have to fix some point X0 belongs to X. For each X belongs to X, we are given a path alpha X in X such that alpha X of 0 equal to X0 and alpha X of 1 equal to X. Let Cx be the range of alpha X. Then Cx is connected since it is the continuous image of the unit interval which is connected. Then clearly we will get X equal to union X belongs to X of Cx. Now we want to show that this Cx is union Cx is connected. For that what we are using is X0 belongs to Cx intersection Cy. So Cx and Cy are not mutually separated. Then by a previous theorem we have studied that one. Union of connected set is connected if and only if the members are not mutually separated. So we have shown that this Cx and Cy are not mutually separated. That means their union is connected. That is X is connected. Now the converse, that is path connected implies, that means this theorem implies that path connected implies connected, but connected does not imply path connected. Previous class we have seen that uh, locally connected, right? Connectedness does not imply locally connectedness. Are you remembering? Locally connectedness does not imply connectedness. Are you remembering that one? Yes, what was the example? We are given an example as com space, right? So there is some problem in this. Okay, some news or something is coming inside. I don't know from where this has opened. Okay, nice. So previous class we have seen that locally connectedness does not imply connectedness. So in the same way, connectedness does not imply locally connectedness. Example was the conv space. So also we know that connectedness does not imply locally connectedness. Example was the conv space. This we have seen. But here what we are going to do is we will prove that connectedness does not imply path connectedness. Reverse is true. Path connectedness implies connectedness, right? So here The example is the topologist sine curve. Okay. Previous class also we have seen this example, but we haven't seen in detail. Right. Here what it means is A equal to the set x comma sine 1 by x, which is points in R2 such that your x value is lying between 0 and 1. And B is equal to set of all y 0 comma y belongs to R2 such that minus 1 less than or equal to y less than or equal to 1. Then x is connected. It is clear that A and B are each path connected. What's the reason? Since it is sine 1 by x, maximum value should be 1, right? So they are respectively homeomorphic to close open interval 0, 1 and this one 0, 1, right? So open 0, closed 1 and unit interval closed 0, closed 1, both of which are path connected. But this x is not path connected since x is not locally connected, right? This topology sine curve is also not locally connected. What is topological sine curve means? We are having your x-axis. So you have got x-axis, again got your y-axis. Now somewhere I will mark my minus 1 and plus 1. So this is my point 1 0, sorry 0 1. And make this point as 0 1, and here my point is 0 minus 1, right? Now my curve is starting from here, right? And somewhere here my point is 1 0. Okay, now somewhere here very close to this only I'm starting. Somewhere it's going like this, 1 coming back, or like this, again it should go like this, then somewhere at this point you should have a peak here, right? So at this point it end here. So this is the topology sine curve. Now here too, when you're having a neighborhood, when you're considering means an epsilon neighborhood and all, we will say no. So like that, suppose we are taking a point somewhere here 1 by or 1 by 2, take 0 comma 1 by 2 and go for an neighborhood of like this, that is b 1 by 2 comma 1 by 4, that is radius 1 by 4 centered at 1 by 2. Again you will get something like a comb space, what you will get here, something like this. And this is also not it's not locally connected, also it is not path connected, right? So you take a point over here, so if I'm drawing it a little bit bigger means it will come like this, that portion. Now if I'm taking a point over here and a point over here, I couldn't find a path which connecting those two, so this is not path connected, right? Since it is not locally connected, it is not path connected also, but it is not path connected. So this is an example of a space which is connected but not path connected. Also it is not locally connected. Okay, hope you understood this. Next, what we are having is examples, right? X be a set of cardinality greater than C. Oh, this is over. See, next example. Let X be a set of cardinality greater than C. C means cardinality of real numbers. That means we can take our power set of real number. Then its cardinality is greater than R, no? So we can have that space, right? Let tau consist of the empty set and all sets of X whose complement have cardinality C or less than C, right? You are having a topological space X tau where tau means tau consists of empty set and all subsets of X, that means X itself, and subsets and A, right? Such that, what is the condition? Cardinality of A complement is less than or equal to C. If this is the condition, means this A belongs to this topology, right? Then it's a topology. It will act as the same way as cofinite topology, right? But as cofinite topology, complement is finite. So here complement cardinality should be not finite. It should be C or less than C. Okay. With this topology, X is connected. With this topology, X is connected. Because every two sets have a non-empty intersection. Every two sets have a non-empty intersection. Unless one of them is empty, right? Thus, for the same reason, every open subset of X is connected. So for the same reason, every open subset of X is connected and hence X is locally connected. However, X is not path connected. So this is an example of a locally connected space which is not path connected. So locally connected does not imply path connected, right? So we have got a path connected, a locally connected space that is not path connected, right? So this is the space here. Now if alpha is a path in X, then its range is connected. Subset of X of cardinality at most C. Then the only such sets are empty set and singleton subsets. Then it follows that the only path in X are the constant paths. So the only paths in X are the constant paths. And hence that X is not path connected. Okay. So here what we are seeing is if alpha is a path in X, it is not path connected that we want to say. So suppose there is a path alpha, then its range is connected because it's a continuous image of closed interval AB, so closed interval 0, 1, it should be connected. Subset of X of cardinality less than or equal to C, right? Then only such sets are empty set and singleton subsets, right? Then the path means either it should be empty or it should be constant path. Next we have proposition. The binary relation defined by X related to Y when there exists a path in X in the space X from X to Y is an equivalence relation. So equivalence relation means you know that we want to prove that it is reflexive, symmetric and transitive, right? Reflexive is very easy because alpha connected to x to x. Can you form an alpha? Nothing but loops, right? X, you can find a loop. So reflexivity is very evident. What about symmetry? Suppose alpha from, there is an alpha from closed interval 0, 1 to some space x, and there is some point x and y such that alpha of 0 is equal to x and alpha of 1 equal to y. Now can you find another path beta? So this means from x to y there is a path alpha. Now can you find a path from y to x? That will be beta. So beta y to x. Can I find a path like this? If I can find means it is called symmetric. It is possible, right? How we can define this? You define beta of t equal to alpha of 1 minus t, right? So alpha, take beta of 0. Beta of 0 means alpha of 1 minus 0. That is alpha of 1. Alpha of 1 means the ending point, right? Ending point is y. So your beta is starting from y, right? Now in the same way, you can have beta of 1. So beta of 1 equal to alpha of 1 minus 1. That's equal to alpha of 0. Alpha of 0 means starting point of alpha. That is x. So beta ends at x. So beta is a path from y to x. That we have shown here. Right? Beta by beta of t equal to alpha of 1 minus t for t belongs to closed interval 0, 1. Now beta is a continuous since it is the composition alpha composition f, right? Where f from closed interval 0, 1 to closed interval 0, 1 as f of t equal to 1 minus t, right? Now this composition of two continuous function is again going to be continuous. That means beta is a path from y to x. Next we want to show that it is transitive, right? For that, what and all we have to assume? We want to assume two paths, right? From x to y and y to z, right? Suppose alpha is a path from x to y. So x to y, this is my x, this is my y. Now from y to x, this is y to z. I have got a path here. This is my z. Now our aim is to find a path from this x to z, right? So this is my alpha and this is my beta, right? Path from, now we want to define a path gamma here. So I have defined my gamma as like this. Gamma of t equal to alpha of 2t, right? Where 0 less than or equal to t less than or equal to 1 by 2. And this equal to beta of 2t minus 1 when 1 by 2 less than or equal to t less than or equal to 1. So here my problem occurs where this endpoints, that is 1 by 2. Will it be alpha of t continuous? Sorry, gamma of t continuous? You calculate alpha of, gamma of 1 by 2. 1 by 2 means, suppose I am using this means I will get alpha of 2 into 1 by 2. That is alpha of 1. That means starting point of, end point of alpha, right? Endpoint of alpha. Now if I am finding gamma of 1 by 2 using this one, so this is beta of 2 into 1 by 2 minus 1. That's equal to beta of 2 to cancel, you get 1 minus 1, beta of 0. That means starting point of beta, right? So from where beta is starting, see this is your beta. Where beta is starting, from this alpha of 1, right? Wherever alpha ends, there only our beta starts. So these two should be the same, right? Even if I'm using this formula or this formula at the point 1 by 2, this would result the same. So evidently this will give you a well-defined formula for finding a path from x to y. See, I have shown that it is well defined. Since alpha of 1 equal to y, that's equal to beta of 0, right? Also, gamma is continuous since it is restriction of continuous functions, right? So evidently this is going to be a transitive relation. Thus, path connectedness is an equivalence relation. That is the meaning of this theorem, which implies path connectedness is an equivalent relation. Path connectedness is an equivalent relation. Okay. Now the path gamma defined in the proof, right? Above is called composite or concatenation. So gamma is called composite, or another name is concatenation. Concatenation of the paths alpha and beta, right? And it is defined if and only if endpoints of alpha is the beginning of beta, just like we are defining compositions, right? Next definition, whenever there is an equivalence relation, it will partitions the entire space into equivalence classes, right? So I will have the equivalence classes like this. So the equivalence classes under the equivalence relation being path connected are called the path component of the space X. So these are called path components. Path components of the space. So we have seen that path connectedness is an equivalence relation, and using that equivalence relation we can partition our entire space into path components. So these are my path components. Now we will have a theorem on the proposition on this path components. A subset C is a path component of a space X if and only if C is a maximal subset of X with respect to the property of being path connected. That means if C is a path component, C is a path component. Path component means an equivalence class, right? And if some A belongs to C, and whenever you are having its equivalence class, A equivalence class, right, which is contained in M, some other one, then either C equal to M or M is not path connected. That means if M is path connected means M should be equal to C, because C is going to be the maximal one. As we are defining in the components, we will say that it is the maximal connected set. So here also, with respect to the property of connected, path connected, this C should be maximal. Theorem, proof of the theorem. Suppose C is a path component of a space X. We claim C is path connected, right? Path component is path connected, that we will say. Let X comma Y, so what you want to assume is C is a path component. path component, we will prove that C is path connected. We will prove that first C is path connected. For that, what we want to use? We want to suppose this is your path and this part is your C, right? Now in C you can take 2 points X and Y, right? There is a path alpha in X from X to Y. We claim C is path connected. Let X comma Y belongs to C. Then surely there is a path alpha in X from X to Y. We claim that the range of alpha is contained in C, right? Then surely there is a path because this is an equivalence class. So two members is there means there exists a path. That's the meaning. Now we claim that the range of alpha is contained in C. So range of alpha is contained in C. That we will claim. For otherwise, that means suppose not, then there exists an S belongs to open interval 0, 1 such that its image, right, alpha of S does not belongs to C, right? We are taking alpha from closed interval 0, 1. Since 0, 1, alpha of 0 and alpha of 1 anyway belongs to this set because starting point and end points, right? So in between this there exists some member such that whose image is not in C. Now define a beta from closed interval 0, 1 to X as we are defining beta of t equal to alpha of st. Beta of t I am defining as alpha of x st. Then beta is a path in X from where to where? Now beta, now this beta is a path from beta of 0. Beta of 0 means alpha of 0 I am getting. That's path from beta of 0, that's alpha of 0 to beta of 1. Now what is beta of 1? Alpha of s into 1, that is alpha of s. So beta is connecting, this is alpha of 0 to alpha of s, right? So this is your beta that I am getting. Okay, that means no. Okay, that means what I get? This alpha can be this s can be related to x, right? That means these two, x and alpha of s, are in the same equivalence class. So x and alpha of s belongs to same equivalence class. We have taken x already in the component, right? So s is also belongs to the component. You're getting a contradiction, right? So showing that C is path connected. Now moreover, if D is a superset, we want to show that it is the maximal one. First of all, we have shown that it is path connected. Next, what we are going to do is we will prove that this is maximal such path connected set. Moreover, if D is a superset of C, then a point of D minus C cannot be joined to a point in C, right? Can you follow this? No. See, this is your C. Now I have taken another set D, which is a superset of C. I want to prove that this C is maximum. Now if this is the condition, if I am taking point over here, that is points in D but not in C. That is, if I am taking a point X belongs to D minus C. Now I cannot find a path which connecting a point over here to here, right? C is a subset of D. So this point, say making X and Y. Now my Y belongs to C, but Y also belongs to D. But there doesn't exist a path connecting this X and Y. So what will happen? We can arrive the conclusion that D is not path connected, right? So D minus C cannot be joined to a point in C by the path in X and containing certainly not by a path in D, showing that D is not path connected. So we have what we have assumed? We have assumed that D is a superset of C, but what we are getting is D is not path connected. Hence, C is a maximally path connected subset of X. So we have proved that the path components are path connected, right? And it is the maximal one. Now conversely, suppose C is path connected and it is not a proper subset of any path connected subset of X. That means it is the maximal, right? Then only 2 points of C can be joined by a path in C. Then any 2 points of C can be joined by a path in C. Hence by a path in X, right? Since enter X we are having a C, right? Now we have assumed that C is a path component. That is, C is path connected and C is maximal with respect to the property of path connectedness. Now if you are having any 2 points, evidently there should exist a path in C. A path in C means evidently this path also lies in your X, right? So your X. Now this path is in X. Now in X also it is path connected, right? Then only 2 points of C can be joined by a path in C, hence by a path in X. Hence C is contained in some equivalence class under N, right? So C is contained in some equivalence class C dash. But as we have just saw, every path component of X is path connected. In particular, C dash is path connected. And what we will get? C is a maximal path connected set. Now we have got that C dash, which is also path connected, which implies our C should be nothing but C dash, right? So C dash is path connected, and so C equal to C dash, but maximality of C. So this altogether forms that C is a path component of X. Okay, so with this I am winding up today's session here. So today we have seen what is a path, what is a simple path, what is a closed path, then what do you mean by path connected space, then every path connected space is connected and converse is not true, that is connectedness does not imply path connectedness. Example is topology sine curve, and we have seen that topology sine curve is not going to be locally connected also. And next what you have seen is another example which shows that locally connectedness does not imply path connectedness, right? Just as the cofinite topology, something like that, you are taken a set of cardinality greater than the cardinality of real numbers, right? Then you're defining a topology in the same manner. Next, what you have seen is being a path connected is an equivalence relation. It will partition the entire space into equivalence classes, and each equivalence classes we will say that it is the path component of the space X, and this path components are maximal path connected subset of the space X. That's the last proposition. A subset C is a path component of a space X Even only C is maximal subset of X with respect to the property of being path connected. So I'm winding up today's session here. Please go through these proofs. Very simple one only. Once you got the logic, it should be very easy for you to study this. So go thoroughly through the proof. And if you're having any problem in understanding in any of the stages of these proofs, please post your doubt or queries in the classroom. Okay. Thank you for your patient listening. Thank you.